So my name is Simon Draper. I'm Professor of Vaccinology and Translational Medicine here at the University of Oxford, and I lead a research group that is focused on vaccine development and antibody immunology, in particular with a focus on human malaria. So malaria is a parasitic disease of humans. It's caused by a single-celled parasite or organism called Plasmodium, and that Plasmodium is transmitted by a specific species of mosquito called the Anopheles mosquito. So malaria causes about 200 to 300 million clinical cases every year, and that leads to just under 500,000 deaths, primarily in children under the age of 5. So malaria not only affects the world's poorest countries, but it also affects the most vulnerable within those societies. So the malaria parasite has a really complicated life cycle as it shuttles between the mosquito vector and the human host. So initially it infects our liver, and then after 7 days in the liver it comes out into our blood and multiplies in the blood, and that's when we become sick. Now, people have been trying to develop a malaria vaccine for many years, and in fact there's been a lot of progress, and we know there are multiple points in that complex life cycle where we can interfere with an immune response. So we in fact now have first generation vaccines that induce very good antibodies against the parasite and stop it getting into the liver. And those have been shown in late stage clinical trials to give moderate levels of efficacy over a relatively short period of time. But that's a big milestone for the field. It's the first time a vaccine has ever stopped a parasite in humans. But what we now need to do is build on that and develop more effective vaccines that also give a longer duration of protection. So it's important to remember about malaria that the organism is in fact a parasite. It's not a virus, and it has over 5,000 genes. So it's a really complicated little animal, so to speak, that is able to change its appearance as it goes through the human host, through our liver and through our blood, and then change its appearance again as it can turn into a sexual form and go back into the mosquito in order to carry on the transmission cycle. There's a really complicated little pathogen, and that's one of the reasons why it's been so difficult to stop by vaccination. So here in our group, over recent years, we've been developing a series of new vaccines. We now have first and second generation vaccines targeting Rh5 in early stage clinical trials. Those have been through phase 1 studies here in Oxford, where we've looked at the safety of the vaccine and the immune responses that it induces, and those have now progressed to similar trials in East Africa, in Tanzania, and now more recently in West Africa, in the Gambia, where again we're looking at the safety of the vaccines and the immune responses, both in adults and the target population, which are African infants under 5 years of age. And the hope is that once we've completed those studies in the next year or so, we will then progress to a phase 2 efficacy study to assess how the vaccine can protect against clinical malaria in the field in African infants. In terms of vaccine development, vaccines, in my opinion, tend to stand a much stronger chance of success of protecting against a pathogen if we fully understand what we need to include. And as part of that, it's really important for us to be able to work on the structure of the proteins that we're targeting for inclusion in our malaria vaccines. And in that regard, being part of the Kavli Institute and our access to really excellent collaborations with structural biologists is a really important part of the work that we're doing at the moment in order to guide the rational design of next generation vaccines.